Welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going to be your host. Today, we're presenting the Milky Way Central Black Hole, Lessons on Astrophysics and on Accretion Physics, by Lena Murchikova. Lena, she's an assistant professor of physics and
astronomy. Welcome back, everyone. Thank you for joining us for today's Law Physics webinar. My name is Alejandro, and I'm going.
Wow, there was a feedback. I was listening. Okay, sorry about that. So let me take it back. Lena, she's an assistant professor of physics and astronomy at Northwestern University, and she holds 2 PhDs, one in astrophysics from Caltech and one in particle physics from Moscow State University. Before joining Northwestern, Lena spent her time at the Institute for Advanced Study and then at Harvard University. And her current research group employs a variety of tools, including observations, data analysis, theory, and simulations. And all of this is to investigate black holes, their accretion processes, and emission characteristics. And today she's going to focus on her recent discoveries related to our own black hole, the one at the Milky Way's galaxy. So as usual, remember that you can ask questions over email or through our YouTube channels, and then the questions will be read at the end of the talk. So without further ado, we'll turn it time to Lena. Thank you for accepting our invitations, and please take it away.
Thank you so much. It's a great pleasure to be here, and thank you for inviting. I don't know, it's amazing to speak with you all today. Let me share my screen, and we can hopefully...
Perfect.
Move to the talk. Great. So today I will talk to you about Milky Way Galactic Center and what we can learn from it about the physics of accretion onto the black hole. Don't worry if you're new to this topic. I'm going to gently introduce everything to you starting from why we should be caring about the black holes at the centers of the galaxy to the Milky Way and its complexity and why is it important. And then at the end, I will tell you actually as a technical talk about the recent discovery. So every large galaxy has a black hole in its center. Those black holes interact with the galaxy and produce winds and electromagnetic emission. Here I'm showing you the pictures of one galaxy blowing a really big jet and another quasar blowing a very big wind. So it is fair to say that the black hole at the center of the galaxy interacts with the galaxy in such a way that it profoundly shapes the evolution of the galaxy and even the universe as a whole, because all of this emission eventually can leave the galaxy and ionize the gas around and send material through the universe. How do black holes actually work and why they do blow winds and why is accretion onto the black holes important? So black holes are very big potential wells. And if you have a potential well somewhere in the universe, material tends to accumulate in it. So then material sitting in this potential well and interacts with itself. It collides and experiences friction. And essentially, it settles in something which would be looking like a disk. And yes, here I'm showing you one of the pictures, is this one, is actually Saturn, if you recognize it. And Saturn's rings are also an accretion disk. If you bend space and time more properly for a black hole, you'll see something like this, and this is an interstellar black hole. So material accumulates in the potential well and interacts with itself and settles in a disk. So then, when the material already in this disk, it experiences friction again with itself. Particles meet each other, scattered from each other. And due to the scattering and interaction, gas loses orbital momentum and keep moving closer and closer to the black hole. When material arrives very, very close to the black hole of I don't know, several tens or so gravitational radii, it swirls like crazy there. And it collides again with itself and getting heated. And this heated material tend to radiate. And so when we talk about black hole emission, we don't actually talk about the black hole itself emitting light. We're talking about this material which is swirling around it and being hot, and that's why it emits radiation. So black hole emission is the emission of the swirling gas around it. How much of the light can a black hole radiate? Turns out it's a lot. Black hole, in fact, can emit about 39% of mc square of material crossing its event horizon. Everything which scales as a mc square is enormous. So, which leads us to this conclusion, just that just a small amount of material which black hole could consume. When I say consume, I mean material which crosses its event horizon, is enough to produce a lot of energy, and material bonded to the black hole and trying to fall in at larger radius is attached to the black hole much weaker. So only by eating a few grams of the gas close to the horizon, black hole can unbound a lot of material on the outside radii. And this you would end up creating winds. So depending on geometry, you can call this jets, you can call this outflow, you can call it winds. So general idea, if it is collimated, it's called a jet. And if it is not collimated and blows material into big angle, you would call it either outflow or wind or whatever else names you really like. What's the purpose? Why do we care about the black hole? As I mentioned, because studies of the black hole, accretion and feedback, accretion is how material falls into the black hole, and feedback is how black hole reacts to this feeding, is what shapes the evolution of the galaxy and essentially the universe. For distant galaxies, when we study black hole interaction with the galaxy, feedback and accretion, we have to rely on the simulations to understand what's going very close to the black hole, simply because we can't see much into the distant galaxies' hearts. We can't see very close to those black holes to really understand all this nitty-gritty of these processes. So we simulate stuff close to the black hole, and more recently there is a big movement to simulate things starting from the galactic level, how the galaxy accreting material and then how it is propagating through the galaxy, and how then we zoom in into the black hole at the center and how the galaxy feeds the black hole itself. But essentially, those are the simulations. Why do we talk about simulations when we would like to talk about black hole theory? It's because black hole physics is very, very complex. And not just because GR is complex, general relativity. It's also because astrophysical black holes surrounded by matter. So if you want to study black hole theory, you need to study its general relativity, radiation transfer, plasma physics, atomic physics, molecular physics, most of the physics essentially, which is too complex to tackle analytically in any meaningful way. So when we discuss black hole theory, we usually imply black hole simulations, because we need to put all of the physics into the computer and see what's going to come out. For most black holes, as I mentioned, we have to use the simulations because we want to know what happens in their hearts. But there is one very, very special black hole. This is a black hole at the center of our own Milky Way. For this black hole, due to its proximity, we can actually see a lot of these processes directly with our telescopes. So Milky Way's galactic center, Milky Way galactic center black hole is called Sagittarius A star. I will explain a little bit about the name later. It is located about 8 kiloparsecs away from us. So that is close enough to resolve the black hole with unprecedented details, which would not be possible anywhere else in the universe. This is the black hole for which we know it is a black hole due to the fact that the motion of stars being tracked around it and show that whatever object is at the center is too small because the stars approaching very close, and very massive because they bend stars' trajectory so much that it can be nothing but a black hole. The small video I just showed you is actually not a simulation. This is an observation of the passage of the closest star to the galactic center. So we also contract smallest clouds orbiting the black hole and to learn what happens and what's the composition of those clouds and what sort of clouds are living in the area and the black hole are available for the black hole to be consumed. As a result, there is, of course, this is a wonderful region to study the black hole accretion and feedback, but there is a bit of a problem here because this is also an incredibly complex region. Why is it complex? To explain it and not be very confusing, I'm going to build your galactic center as structure by structure, and we're going to discuss them all together, and then we'll see the complexity and discuss what it tells us about the physics of the black hole accretion. So I'll start by flying you into the galactic center. So galactic center is best visible from the southern hemisphere. It is located in the constellation of Sagittarius, and that's why a black hole called Sagittarius. It's called A star because A was already taken, so that's had to be Sagittarius A and a star. It's covered by the dense dust clouds because we are in the plane of the galaxy and we're looking through the plane of the galaxy when we're looking towards the galactic center. So right on the side of the structure is the bright radio object. And that's our own galactic center black hole. Now I'm going to plot you schematics with every structure being added one after one. So first we start with the black hole at the very center. You see east and west are flipped to the normal maps because that's how we do it in the sky. So the black hole at the center is Sagittarius A star. It has a mass of 10 to the 6 solar masses, 4 million solar masses. And while this mass sounds large, this black hole, in fact, is quite small by the central black hole standards. And when the black hole is small, what happens is that its characteristic time scale, namely the time scale of material orbiting it, so which leads to characteristic changes in the emission from the black hole, is relatively short. And for our own galactic centers, those scales are very, very human. This is about 30 minutes. So we can look at our black hole and literally see how it breathes with approximately 30 minutes on a 30 minutes time scale, things will be changing. So that's very convenient for observations from one point of view, for observations in real time. For other things, it's much harder because you have to integrate, and it's making a whole mess if you have to integrate many hours of a variable object, but that's a separate subject. So anyway, it's a very human time scale. We can see things changing around it. That's great. So what happens else around the black hole? Around the black hole, we have a big cluster called nuclear star cluster of several million solar masses, several million stars, several million solar masses. Most of its mass is close to about 1 parsec, and then it's kind of gradually goes away over, you could say, about 5 parsecs. So how does the nuclear star cluster look like? Everything I'm plotting here is to scale, and the images I'll be showing you are to scale. So this is a nuclear star cluster. So you can see there are a lot of stars there, and it's very dense region. Okay, so nuclear star cluster is here. And then this yellow line appeared. This yellow line is the plane of the galaxy. The coordinates I'm showing you this schematics in is the coordinates such that that's the plane of the sky. For those of you who are astronomers, I'm showing you everything in array and deck. I also showing you the markers of how things rotate. When you see a dot, it's like you can imagine an arrow pointing toward you. So at the bottom, that part moves toward me. And when there is like a cross, it's moving away from me. So it moves from the bottom of the screen across the screen and goes away on top. That's the rotation of our galaxy. Okay, next big structure is the mini-spiral. Mini-spiral is a free streams of gas at temperatures of about 10 to the 4 kelvins. It's ionized gas. It's hot. It's about the temperature of the sun. But for this particular region, where a lot of gas, there is also X-ray emitting, this can be considered cool. So I will mention, when I mention this gas, I'll be saying cool ionized gas. But you should know it's 10 to the 4 Kelvin. That's the temperature of the sun. So a mini-spiral is composed of free streams of gas carrying material towards Sagittarius. So again, with the rotation, the upper arm goes behind me, if I'm a Sagittarius, goes behind me, goes down, and comes somewhere on the side. The arm, which is horizontal, again goes away, comes behind, and comes forward to the front. And one of the arms, the vertical, which goes down on the right, this one doesn't have rotation markers because we actually don't have rotation knowledge about this arm. I actually showed you the picture of the mini spiral before, but that's a different picture. They see all the three arms, and that's an observational picture. So, and this is a red object here is a Sagittarius itself. All right, another structure which just appeared is this red circle, which is a circumnuclear disk or molecular ring. This is a gas structure which is the biggest in this inner 2-ish parsecs of the galactic center. It contains gas with temperatures from several between 10 to 1000 kelvins, and it contains molecular gas. So how does it look? That's it might be confusing, but this is a lot of molecular gas, and you see that ring which I just showed you, and it's kind of rotating, and that's blue mean moving away from you, red moving toward you, and that's cut of the most dense region of the molecular ring. So this is the molecular ring, and this is an observational image again. So another structure appears on the screen is the purple oval, which is a clockwise stellar system, which contains a group of Wolf-Rayet stars. which are blowing winds, and most likely a dominant source of the hot X-ray emitting gas in the region. All of this region, all of the structures I showed you are swimming also in the hot X-ray emitting gas. This is a picture of X-ray emitting gas at temperatures about 10 to the 7 Kelvin and higher. This is a Chandra image, the Sagittarius at the center. And if I overlay the structures which I showed you before, here they are. Some of the structures, particularly this one, is actually not in the galactic center. It's just a projection effect. So, but everything is swimming in hot ionized gas, X-ray emitting gas. So let me zoom even closer. For X-ray emitting gas, we're going to define so-called Bondi radius. Bondi radius is a radius at which temperature of the gas, the velocity of the gas due to its temperature, are no longer enough to escape the gravity of the black hole. So essentially, things which are within the Bondi radius are kind of destined to fall into the black hole and be captured by it. So Bondi radius is about 1 arc second or 10 to the 5 gravitational radii. And that's right here around the black hole. And I'm making a zoom in of this region. Inside there, we have a S cluster. S cluster is this group of stars which are orbiting galactic center, and they being tracked. And for the tracking of the stars, Andrea Ghez of UCLA and Reinhard Genzel of Max Planck Garching got Nobel Prize. It's because that was the proof of the study of the black hole. So that's the famous S cluster. So for the scale, that's the star I showed you previously passing the closest to the black hole. If I can again get a little cut. So this is the black hole and this is the star passing. It depends on the day. So this is just to scale in this region. This is the structure of cool ionized gas well within Bondi radii, which is visible on ALMA observations. And in general, when we say that galactic center region is very complex and dense, what we mean is the following. Here, this red arrow shows you to scale the distance between the Sun and Alpha Centauri. Meaning that within the distance from us to our nearest star, where essentially not very much going on between us and them, we have a million star cluster, 4 million mass stellar mass black hole, and bunch of these heavy and complex structures, arm and streams and central. So that's why when we say it's a complex region, we mean it is crazy dense and crazy complex region. So why do we care about the Milky Way's black hole again? We care about the Milky Way's black hole because it's our best window into inner working of the galactic center black holes. Because there is no other black holes we can see in such details. There is no other black hole for which we can study and try to understand its behavior and test our theories, because we can measure something we predicted immediately right there. And it's something which breathes with the approximately every half an hour, meaning this system is like essentially kind of live. We can see it changing in real time. So I showed you all this complex picture, which I built one by structure, and there is lots of things going on here. Lots of things are rotating and have tons of different gases. There is one thing which is not on it, something I mentioned at the beginning of the talk, is that black holes produce winds, right? In fact, when we simulate black holes, there is no simulation of a black hole which doesn't produce wind. So for Sagittarius itself, if we assume current estimate that its accretion level at the horizon is about 10 to the minus 8 solar masses per year, and accretion within this Bondi radius, which I mentioned is the capture radius for X-ray emitting gas, is 10 to the minus 6 solar masses a year, which leads you that more than 99% of mass m dot, the mass which is heading toward the black hole, must be blown with the winds. So, but on the images I showed you, there is no signatures of that winds going. You might wonder, well, the winds, sorry, let me switch back. So the winds were essentially predicted when this object was discovered. That about 50 years ago, soon after it been discovered, people say, great, the object which emits that much radiation must be blowing sizable winds. But the wind has been missing since. You might say, okay, what if our black hole is just different and our theories are wrong in a way that our black hole just does not have wind? Well, we can disprove you by showing you this. On a large scale, when on a large scale, I mean on a scale of the galaxy, there is no lack of signature of past activities from the black hole. You see Fermi bubbles and gamma ray. So this, it's a gamma ray image. So this blue line, it's actually the galaxy itself. It's just thin. We have this galaxy. And this structures, purple, are Fermi bubbles. They extend about 15 kiloparsecs out of the plane of the galaxy. So clearly, and somewhere around the Sagittarius, because that's somewhere there. Great. There are also Erazita bubbles in X-ray, so that's the plane of the galaxy. I'm orienting it the same way and I was orienting you the previous image, where the plane of the galaxy goes sideways. So to avoid any confusions. So you see those bubbles. They are also sitting more or less on top of the galactic center. And they're also clear signature of something was going on. On the smaller scale, there are X-ray chimneys, which are about 150 parsecs. Again, oriented the same way. This is one chimney, that's the other chimney. So what's clear is that galactic center clearly doing something and blows these bubbles. So it does have winds, at least occasionally. But the trick is that on a scales of about 1-2 parsecs, where we can like literally look at the galactic center and see some evolution, we don't have any consistent signatures of active outflows. When I say consistent, I mean there are signatures and multiple claimed outflows, but they are in different direction. And on the different direction, it wouldn't be just direction which are a little bit different, it would be direction which in the plane of the galaxy, perpendicular to the plane of the galaxy, toward the observer at various degrees, at 45 degrees to the plane of the galaxy. So they are really all over the place. So it would be fair to say that there was no consistent signature for an active outflow. Well, but I'm going to be pleased to tell you that actually we did found the wind from the galactic center. And that's what I'm going to tell you for the next 15 minutes about. This is the work joined with Mark Gorski, who used to be a CIERA fellow at Northwestern and who is now a research assistant professor. By the end of this part, I'm going to try to convince you that there is a big wind coming out of the black hole, which is marked with those lines. It's about 1 parsec cone visible. And explain what it means from the general perspective of the evolution of the galaxies in the universe. So, but this part is going to be weird. So to tell you the story about the discovery of the wind, I actually must tell you 3 separate stories. One would be about reimagining a good old data analysis technique, which led to dramatic improvement. Second story is about applying this technique to something everybody seemed to forgot for 30 years. And the last story is about finding a solution to a 50-year-old puzzle, which, as a disclaimer, is going to be our discovery of the winds. With this, I'll start by telling you that interferometry is hard. So interferometer is different from normal telescope by the following. You can imagine it this following way. When you have a normal telescope, you have a lens or a mirror. Let me say a lens. It's a big lens, the radiation falls on it. In fact, you can do the calculation and figure out that the field from the distant source, which falls on the surface of the lens, is actually a Fourier transform of that source. But how do you see the image of the source behind the lens? Is because the lens itself doing the inverse Fourier transform and reconstruct the image. That's actually what the eye is doing. What falls on the surface of my eye is a Fourier transform of what I see, especially for distant objects. That my eye is doing inverse Fourier transform and produces the image. For interferometers, we collect information on the surface of this lens. And so we have to do the Fourier transform using computers because the lens is not going to be doing this job. Moreover, not all of the surface of this lens is used. We kind of throw a piece of cloth on top of it with only some holes. And that's going to be your telescopes. So interferometer is a group of telescopes spread across the surface on the planet in different places. I'll particularly be talking here about ALMA observation, which is ALMA is a telescope in Chile, Atacama Large Submillimeter-Millimeter Array. ALMA has 60 telescopes. They're spread on the Atacama Desert in the plateau. And we collect information from all this telescope, to correlate them with a computer, which is called correlator, and we'll get an image which we'll then work with. Anyway, so because of this structure of the telescope, which it collects information only at the points, various points, then we have to process the data. Interferometers has a very complex reaction to point sources. So here's an example. The example on the left here. The telescope reaction to a point source. This exact picture going to depend on in configurations of your antenna, but like this is particular one fits the image I'm going to show you on the right. So how do we ideally what we want, right? When we observe with the telescope, we want to observe a very bright source somewhere, calibrate the response in a preferably empty part of the sky, calibrate the response of the telescope, then go to our field which we're interested in study and observe it and integrate. And so using the knowledge we just used for calibration, we reconstruct the image. Unfortunately, that's not how it always happens. And sometimes we have very bright sources, which are brighter than anything around them, in the middle of our own image we want to study. You can see that those sources going to create this weird artifacts across the image, and if we want to study faint structures around them, it's already going to be hard. But now I'm adding the complexity of the source being variable. like Sagittarius. About every 30 minutes, it goes up and down. So that pattern on the left is going to be brighter and fainter while you are observing and integrating at different moments. And moreover, the sky is rotating, so this pattern is actually going to be shifting. So what is the result you're getting is this is the pattern of reaction of a telescope to a point source. And on the right is a beautiful press release image from 2021. And if you have dark room around you, you can see identical patterns to the one on the left spread across the image. That's the same structure. You see those lines going here. You see a bit of like chaotic lines in here. And that's the same pattern imprinted here. Meaning you should be obvious that to study faint structure around the bright source is a hard job. Because what you need to do is to not confuse that, which is an artifact, with the actual distribution of gas and various streams around. So again, I'm pleased to report that we solved this problem. This problem, people tend to focus on solving this problem at the point where you create the image of the source, which is the point where you do Fourier transform from your data into the produce, Fourier transform and the actual image to which looks like a source. We went a step backwards, and we fixed the issue at the point of calibration. So it is I'll very briefly summarize the approach, and if any of you are working on interferometry have similar issues, please let me know, and I'll be delighted to talk to you about this, and we'll be able to help you to make your images. So what you actually need to do is to first embrace your strong source and understand that it's actually a gift for you, because you can use it to your advantage. So what you need to do is you need to determine how the source varies. You can create the model of the source variability. You can then use this model to calibrate your data using your own data, not to separate sources. You can use the own data, you can do self-calibrate on this data. Then you would use the knowledge of the source about its variability to remove the source from the data at the before Fourier transform at the UV plane at the telescope level. And then you can image everything except the bright source. There'll be nothing to spread your artifacts. And you can get wonderful image. So to summarize, it's like use your strong source to your advantage to calibrate, but under no circumstances, please do not image it. And that's what we did. So the goal of this exercise was originally to create the most accurate map of the ionized gas of the Milky Way. And this is, here it is. It's still in preparation with Mark Gorski, as I mentioned. So you can see that there is some sort of, something look like a thick line going around all the structures. Well, there is no thick lines on this image. It's just contours piling up, identifying you where the edges of the streams are. I don't know. I think it's quite cool looking that you see such a big difference between the background and the streams of the mini spiral. This is a mini spiral. This is one arm, second arm, and the third arm going down. All right. But while we were doing this, oh, by the way, yes, I forgot to say that the resolution of this image, if you look at this beautiful place, that's the resolution. So, but while we were doing this image, we noticed something interesting, which brings me to the next topic of applying this technique to something which people forgot for 30 years. In 1994, Marshall and Lazenby say that no one can see a particular molecular line, CO line 2-to-1 transition in the galactic center. So CO molecules is very interesting because that's the strongest chemical bond existing in nature. So these molecules survive at high temperatures, they form at lower temperatures, so they have these rotational transitions which are sensitive to temperatures from starting from 5 Kelvin. This particular, and they dissociate at about 5,000 Kelvin. And this CO2-1 is sensitive, particularly sensitive to molecular gas at temperatures about 100-ish Kelvin. So we had this line in our ionized gas observations. And when we were imaging ionized gas, on the sides, we saw structures which we knew belonged to the galactic center because they had names and they were perfectly overlapping with the, say, known age of the molecular ring and with exactly the same morphology. But Marshall Lazenby in 1994 told everybody that CO2-1 cannot be seen in the galactic center, and since then all the proposals asking to observe this line in the galactic center has been denied, with reference to this paper that you cannot see anything in the galactic center. So I must mention that they observed the galactic center with a resolution about 80 times lower than ours. And obviously technology by then was nowhere comparable to ALMA in sensitivity. So anyway, we saw there is we were told there is you can't observe anything, you can't see anything. We clearly saw something. So we imaged this line anyway. Because it was in the band, we wouldn't be getting time if we asked for it. So what we saw was this big structure. So what you're looking at is the deepest molecular gas map of the galactic center by a factor of 200. That's a combination of about order of magnitude improvement from the technique and another order of magnitude improvement from the line, which is very bright but have never been actually studied with a very good telescope. When, I'll show you something like this, and it's the first discovery experiment, you would go, oh, come on, something must be wrong with this image. So when this happens, first discovery, you overlay your image on everything you can think about. So first, you stare at the image and realize that some structures you see actually have names. And they are identical by the shape to the structures detected in different lines. Well, there's one called Triop, the other one called SEW. I'm actually not sure what it stands for. It's like, okay, that's clearly something. Then you can overlay it with the map of the molecular ring because it's a big ring which is rotating. Here it is. You can see it. That's the big ring. And the region we're observing is inside, and it's limited by how much 12-meter antenna can see. ALMA composed of 12-meter antennas, and the field of view is about 1 parsec. And you can see if I overlay known data of the molecular ring with our new data, they match perfectly. The edges on top of the edges, the rotation is exactly where it's supposed to be, right? Moreover, if I then overlay it with X-rays, because X-rays are emitted by very hot gas, and I'm talking here about cold gas, which is 100 Kelvin. So X-ray emitting gas and cold gas clearly should like each other, and should be some anti-correlation preferably. And here we are, there is anti-correlation between X-rays and cold molecular gas. They clearly don't like each other. So the result out of this particular discovery is that first, molecular ring has been always considered the structure which does not have any molecular gas at the center. It's written in the reviews, but we can clearly show that it's completely filled with the molecular gas because molecular gas just rains from it. Moreover, it approaches the black hole very close. This distance is similar to Bondi radii, meaning in this radii not only X-ray gas feeding the black hole, but also cold molecular gas. We already knew that the cool 10 to the 4-ish Kelvin gas is also feeding the black hole in this radii. Anyway, but let me move to the last part. I showed you this map already, but I didn't point at the morphology of it. You see this big gap in it. In the rotation map, where the colors mean the velocity, that's the same place where you have a lot of chaos in terms of the velocities, meaning there is not much emission, but a lot of like chaotic movements. So one thing black holes do not blow from the center is a cold molecular gas. Black holes tend to blow winds close to them, and it's going to be hot winds coming out. And this hot wind would not like meeting the cold molecular gas and would carve a hole through it by either moving this molecular gas out of the way or heating it, meaning turning it from cold molecular to something else, which will stop being shown in these images. So moreover, if I again overplotted as a molecular ring, this structure is this the wind we identify, and I overlay on the mini spiral, one arm, second arm, third arm. You see that the direction of the wind coincides with a known cavity, which you wouldn't spot on the screen, like specifically related to the black hole, because there are many structures like this, right? There's a little bit of cavities here. But this fits perfectly, and moreover, it lands exactly where the third arm of the mini spiral is, which has been long time considered that it's probably a not actual gas stream, but an ionized edge of the molecular ring, ionized by something. And so now we say it's ionized by the outflow from Sagittarius A star, from the black hole itself. So, summary about the winds is that large-scale wind from black hole has been proposed since 1970s, and in 25 it finally was found. It's a funny looking one because it's neither perpendicular to the plane of the galaxy, and it's not perpendicular to the molecular torus or circumnuclear disk, where majority of the mass is, and its mass which is feeding that region the most. It's also the winds seems to be asymmetrical because we can clearly see one direction. The second direction, there is excess of emission here, right? But there is not such a clear conical structure. So the wind must be asymmetrical, which is actually not a big problem because in cases where you have accretion colliding with your outflows, the outflow can turn. And here is my conclusion about what because my talk was called Milky Way's galactic center, what can teach us about black hole accretion and feedback. So what it can teach us is the following. Think about this from this point of view. Sagittarius A star, our own galactic center black hole, is a typical representative of a class of underfed black hole. Quiescent, quiet, they don't do much. But it's a dominant state of the black hole where they spend majority of the time. So when you see these big quasars, big jets, those happens only for a short period of time, after which black hole goes quiet. And it lives in that state. So our findings reveal that inner accretion zone, inner accretion environment is incredibly complex. So molecular gas, cool ionized gas, feeding the black hole, not at some amorphous distances where this gas just falls there, get heated, and then propagate over the black hole as X-ray emitting gas. It feed the black hole well within the Bondi radii for the X-ray emitting gas. Meaning that's where we mostly concentrate on the simulation, but there are 3 phases of the gas present there. Moreover, black holes do always form winds. That's great. That's what we expected. but the wind direction is not fixed. And because it's very weak, it's very dependent on what material falls in and how it bends. And so most likely in states like this, the winds from the black hole kind of swinging around the galactic center of all of the galaxies in general and depositing the energy all over the center rather than in one particular direction, which we tend to usually assume to be somewhere close to perpendicular to the plane of the galaxy. And so Sagittarius star was supposed to give us a window into the inner workings of the black holes, and I believe it did. And I want to point out that none of this importance of the cold gases been well studied for the black hole accretion, because we pretty much see it for the first time. And with this, thank you so much.
Thank you, Lena, for this wonderful talk. Let me see, there's typically a delay with questions.
Sorry,
This was
5 minutes.
lovely. And then maybe there are questions here from the coordinators. This was lovely. I have lots of questions. Perhaps one of the things that you alluded at the beginning, but maybe I didn't follow, is there any connection between the wind and a jet, or these two things should be completely separated? And if I may ask, if there is a wind, if there should be there a jet then also, and what are your thoughts?
So wind and jet is the just two names for the same phenomena. So when the black hole create an outflow, which is a general can be called the wind just because something comes out. If whatever comes out is very collimated and comes out as a line, something look like a line which is like long but thin, it's called jet. The bound and otherwise it's not called jet. The boundary between what is called jet and what's not called jet is actually not very well defined.
Mhm.
It's just the same phenomenon. The jets tend to be more magnetized, and that's why they manage to propagate in a more straight line, at least out of the black hole. But otherwise, it's the same phenomenon. It's just not very magnetized and not very powerful black
I
hole
see.
below something much bigger.
Okay. And do we have any observational evidence of a wind in another system that has, let's say, the same kind of position of the one you discover, in the sense that it's blasting a little bit the plane? Is that because
So,
you alluded about dynamics, but then so in some sense, yeah, do we have an example of a wind that has that direction, let's say?
so for other galaxies, we do see sometimes that the jets are not perpendicular to the plane of the galaxy, they're a little bit on the side. But what you should understand is that when we're talking about other galaxy, we're talking about something which was powerful enough to exit the galaxy.
Mhm.
So if you're talking about the galaxy, say
I
it's a
see.
deep galaxy, right? To exit the galaxy, there is only way for you to exit is fairly close to be perpendicular to the plane of the galaxy. So things like winds which are so pathetic that don't barely leave the galaxy, we literally probably can't see in other galaxy at least much. We can see a little bit of the effects, but not at such a close proximity where we just like, okay, this thing dies within. This thing probably dies within inner like 2 parsecs,
Okay.
which is about 10 to the several 10 to the 6 gravitational radii, which is not something we can easily explore for other distant galaxies.
Okay. And a little bit related to those questions is that, do you think we can use that wind to say something about the inclination of the source, or typically they can be decoupled, and because of the variation, we cannot know anything about the rotation axis of the black hole?
So I would like to agree with you here, yes, because it's clearly weak and it's clearly bending, and you clearly see that two sides are not exactly the same. Clear indication the wind is bending. So whatever left the black hole then collided with the stuff and then it bended.
Okay.
So it is possible, I would assume, to try to zoom in closer and closer and see how it's going to track, but not on the scales which I showed you.
Okay.
I can, like, I'm willing to bet that the spin of the black hole is not aligned with the direction of this cone.
Okay. Cool.
It's definitely at a sizable angle to it.
Wonderful. Okay. Let me check something. I think I received a question. Let me try to rephrase it a little bit. I guess this question is asking why do you see just one and not one in the back as well, or should there be wind also going in another direction?
So wind is supposed to go in two directions. So I
Yeah.
can clearly see, let me see if I can just go. Yeah. So I can clearly see one cone, which is a really clear cone. The other side has also lack of molecular gas emission and excess of X-ray emission, right? But it's not that clear. It's like perhaps this is the cone. There is another situation is that you see it cleared through the plane of the molecular ring, right?
Yeah.
Molecular ring has, you can't see here because it's just rotation, but molecular ring has more material on that end and less material on this end. So there'll be less material raining from it on that end. So it would be harder to track the clear cone through it.
Okay.
So if you would ask me to guess, I would say second cone goes like this.
Okay. Thank you. Let's see if there is a follow-up to that. Although I do have a follow-up. Is that and that is a totally possible scenario that the jet is that asymmetric, like it's going like I don't know this many
I
degrees.
think, let me see, I think I had it earlier. I had a plot from the simulation. Sorry about this. A lot of things. Don't break. Don't break on me right now. You can, oh yeah, so
I see.
yeah, absolutely. Moreover, it's completely unrelated simulations.
Yes, yes. Okay, cool.
But yeah, you can definitely see like one cone would be clear and visible,
I
the
see.
other one would be kind
Yeah.
of dead and barely
Okay,
visible. So yeah, nothing special.
cool. Is there any question here from the coordinator? Joel, please go ahead.
Yes. So you mentioned that the black hole shows variations of the order of minutes, right?
Seconds, yeah, yeah.
So what would we expect of the wind? So how often would you expect the wind to change in any way?
So when we talk about black hole variation on a scale of, like minutes, seconds, it's very close to the black hole on the scale, I don't know, of 10-ish gravitational radii. The wind is more like a cumulative effect. There'll be something changes very close to the black hole, but nothing would change on the scale of parsec when it is just like accumulated over years and years. So yeah, very, very close to the black hole, you should be able to see something, but it's a very weak wind, so it's going to be hard to see very close to the black hole when there's so much bright emission. But yeah, on parsec scale, it's just different time scales and everything averages out.
I see. Super. Many thanks.
So I think I have 1 minute to ask you the last quick question, and then we finish at the hour. It's in a 1 minute sentence, Lena. What do you mean by like a model for the source variability? In the sense that you are using that data, you see everything, but then you want to model the variability, but then in some sense you are also modeling everything else. So what do you mean by a model of the
Oh,
variability?
you can extract variability. So the telescope standard, so ALMA is great because it has very
Yeah,
standardized. So ALMA goes to observe calibrator no matter what.
I see.
Doesn't ask your opinion. ALMA will go and observe a calibrator because everything is standardized.
Uh-huh.
It already it's very hard to calibrate on that source really well because if you want something very faint,
Yeah.
you can tell after ALMA went to calibrate on that, so on the calibrator, and it returns to the field, your central very bright source, you can extract, like, it's already enough for you to extract every second what ALMA dumps as
Okay.
observed flux. And then it's going to be a bit scattered, so you want to average it to be a bit smoother, right? Because you don't want to calibrate on the node.
Yes.
And that's what the only thing, I mean, you pretty much don't do much modeling, you just extract variability, you feed it, you calibrate through it. You can do it iterative process because you say, well, I believe my source is that, and like show me how it's going to look, and it's going to correct
Okay.
mistakes in the image, so you can actually do it iteratively, and that's going to be better. So I use model rather than extracted.
I see. Okay. Cool. Well, thank you, Lena, for sharing this very exciting discovery. Congratulations. This is great. And as you said, this is more things will come, and we will keep understanding this old source with new data and new telescopes. So thank you for joining us and giving us this law physics webinar.
Thank you so much. It's been a great pleasure to be here.
Thank you. For the rest of the people, please stay tuned for our next webinars. There are a few more this semester, and then we will come back. So please check the calendar for upcoming talks. Thank you, everyone. Good to see you. Okay. Good. We're not live anymore. Thank you, Lena. This is exciting. I mean,
That's very good and very, 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 very interesting.
And